Good afternoon, this is Mr. Schweitzer, and here we have a quick video. Well, this one might take a little bit longer, but on calculations involving the equilibrium constant K, involving Kc and Kp. Alright, so a mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472. Keep in mind this temperature is only here because the K is dependent on that temperature, meaning that if we change the temperature, the value of K will change. The only way K will change is if we change the temperature. The equilibrium mixture of gases, when it was analyzed and found to contain 0.12, okay, so we have a value of H2, N2, and looks like we got some NH3. So right here we have our equation. If the equation is not easily accessible, as a general I'll rewrite the equation, but I have initial stoic ratio N. I'm always going to write out my K. I'm using molarity, so it's Kc equals the concentration of my NH3 squared, concentration of H2 cubed, concentration of N2 to the first. You want to be very cognitive of the fact that they're giving me equilibrium mixtures. That means it goes right here. They could also give you initial mixtures. At this point we have H2, which is 0.0402. Also keep in mind it's giving molarity. I track molarity. K is tracking concentrations. So I want this to be the molarity or partial pressures if you're dealing with Kp. 0.1207 and 0.00272. These values then get plugged into the expression. I have the NH3, which is 0.00272 bracket squared. I have H2, which is 0.1207, and then I have 0.0402, and it would be the H2, which is cubed. Yes, cubed. At this point we plug it into our calculator, and I get I'm getting a value of, if I did this correctly, which I hope I did, just calculator wise, 0.94. You can check my math and see if I made a mistake. 0.00272 squared divided by 0.1207 divided by 0.0402 cubed. Alright, next one. Now, a couple things I might note about this number. What is that? It's a K value. K value is simply a fractional value that is a fraction of the concentration of the products over the concentration of the reactants. This is simply a number that tells us where are we on our relationship between the reactants and the products. And this thing to me, if one is right in the middle, then I'm just a slightly reactant favored. Okay, in this case, a mixture of H2. Now at this point I have only dealing with moles. So that's something I want to be aware of. I want to be in moles per liter. It's a 5-liter container. They're giving me mixing them, so these are initial conditions. So here's my equation, initial stoic ratio ending, and I want to plug in my initial concentration. Now this is 5 e negative 4 negative third moles of H2 in a 5-liter container. So 5.0 e to the negative third. Now they're holding 4 sig figs here, so be aware of that. Divided by 5 liters, and of course it's 4 sig figs, so this problem is holding 4 sig figs throughout it for every value, although right here we're dropping to 3. So in the end I would want to hold 3. Alright, so I got 5 divided by 5 is 1 e to the negative third. I'm not showing all my sig figs here. And then I got the next value is going to be this guy, which is 1 e to the negative second divided by 5. That's 1/5, or 0.2 e to the negative second. and there's nothing of the H2. This reaction will shuttle this way to achieve equilibrium. Stoic ratio is going to be minus x plus 2x, and these are the, as it shifts to attain equilibrium, it will shift in this stoic ratio. Alright, I want to solve for x in this case, but I will use one more piece of information here. It says I have right here, it says this value is going to be 1.87 e to the negative third, and now this is the key that unlocks this entire reaction, because I knew I had 0 to begin with, and now I'm ending with this amount. Then that means that this value is 2x. So in this case, I have 1.87 e to the negative third equals 2x. Divide out by 2. 1.87 divided by 2, and I get 9.35 e to the negative fourth, or 0.93 negative third. Now that is equaling x. I can then plug this value into these guys, and you would take this guy, you subtract this guy off. That's what you lost as it shifted to the right, and I have this value left, and I have this value left. So take your values, plug them in. 1 e to the negative third minus 9.35 e to the negative fourth is 6.5 e to the negative fifth, and then this guy is 0.2 e to the negative second minus 9.35 e to the negative fourth is 1.06 e to the negative third. So I now have all my values for my equilibrium conditions. I can then plug these in to the equilibrium expression, and I'll have my K value. This is going to be 1.87 e to the negative third squared over 6.5 e to the negative fifth times 1.06 e to the negative third. Plug all those out, and we'll have our K value. 1.87 e to the negative third squared is 3.49 e to the negative sixth. Divide that by 6.5 e to the negative fifth. Divide that by 1.06 e to the negative third is K equaling 50.7. Again, this is a value to me that means it's slightly product favored. Number is not just a number, that number has some value. Alright, scrolling down to the next problem. A reaction mixture of three gases A, B, and C are all 1 molar at 200 K. The reaction below runs from a period of time and forms an equilibrium balance where the solid product formed at the bottom, the concentration of A at equilibrium is 0.5. So initial stoic ratio equilibrium. D doesn't have any concentration, so we're just starting out with this container. Whether it's opened or whether it's closed, we don't really care. But it's got A in here, it's got B in here, it's got C in here, but there's no D to start with. There's 1 molar of this, 1 molar of this, and 1 molar of this. So we cannot, this thing cannot shift to the left because there's no D present. I mean, it doesn't need it. It's not counted, or it's not measured to attain equilibrium concentrations, but we still have to have it. In order for us to go to produce B or A, we would need to consume D to go this way. So if there was some D present, I would be able to shift either way. But in this case, I cannot shift to the right, to the left, because of the lack of D. They give us more information here, saying, okay, piece of some time has gone by, and the concentration of A at equilibrium is 0.5. And this is the key to what we have here. It unlocks everything else for us. Minus 0.5, minus 0.25, plus 0.5, 0.25, and I will gain some amount of this D, but I don't know the volume of the container, so I can't find the moles, and therefore I can't find the amount of D that I will get, but I will get something. This would be 0.75, and this would be 1.25. And it wants us to write an equilibrium expression, so it would be K equals the concentration of C, concentration of A, squared concentration of B. Complete ISC table. I did that. Determine K. Let's do this. I got C, which is 1.25, A, which is 0.5 squared, times B, which is 0.75. And we get 6.6 and equals my K value if I minus any mathematical errors. Let's go to the next one. The following reaction goes to equilibrium at 500 K. Original pressure of A is 0.55 and reduces to 0.15 at equilibrium. The original pressure of A is 0.55, reduces to 0.5. Okay, so write the expression. Assuming that it says the following reaction goes to equilibrium. Okay, this guy right here. All right, and we're giving us information: initial, stoic ratio, end. We're using pressures here. So in this case, I have the original pressure is point of A is 0.55. It's saying there doesn't say anything about B. Of course, B and C are products. Alright, so there's nothing of this and nothing of this. I will lose X of this, gain X of this, and gain 2X of that, and gain X of this. This would be 0.55 minus X, and this would be 2X and X. But in this case, they're saying this value right here, which is equal to 0.55 minus X, equals 0.15. So what is that value? In this case, this thing drops down to 0.15, and we can find X at this point. So again, just subtracting off, what is X? It's in this case, it's is 0.0 well, hold on. 0.4, yes. So X in this case equals 0.4. So a couple things they want here just to solve the things they're looking for. Write the equilibrium expression. Okay, so K, because we're using pressures, I'm going to use Kp equals, this is looking like a solid, alright, gas, so it's going to be B, the pressure of B squared divided by the pressure of A. Alright, in this case B is going to be 2X, which is 3.30, and this could also be, I'm gaining this amount, but it's a solid, so there's no concentration to gain. It's going to be involved in moles or mass, a non-concentration item. So B is going to be 0.30 squared over 0.15. Alright, so 0.3 squared divided by 0.15 equals 0.6. I now have my equilibrium expression right here. That's this thing here. Did the ACE table determine Kp right there? Alright, this is the Kp. Challenge. If the container is 1 liter in size, determine the mass of carbon. Okay, well, it's not much of a challenge. I think we can do this. I'm going to produce X of this thing. X is equal to 0.15 moles per liter. And since I only have 1 liter, I will get 0.15 moles. And then 1 mole of carbon weighs 12 grams. So 12 times 0.15 is 1.8 grams. An equilibrium was established, reaction of CO, water, carbon dioxide, hydrogen at this temperature. There is an industrial importance of preparation of hydrogen, okay, blah, blah. Alright, so equilibrium is found, the concentrations were found in the direction of this. So this couple things here, at equilibrium, these are concentrations. What's the Kc? Alright, so let's rewrite our equation. CO, gas, plus H2O yields CO2 plus H2. All of these are gases, right? But we're using concentrations, so we're doing a Kc. Kc is equal to the concentration of CO2, concentration of H2, concentration of CO, concentration of H2O. Notice that we have water is gaseous at this point. High temperatures, I guess. And they simply initial stoichiometric ratio equilibrium. They give us the concentrations at which we just simply plug in here. Plug them in, and we get 0.15, 0.20, 0.18, 0.041, and punch it out. And my calculator is giving me a value of 4.06, including my K value, my Kc for that matter, just because it's calculated in moles per liter. And that is 1 through 5 of this page, and good enough for now.